we stop at 8:30. And so now we change topics and we go to artificial atoms and from the color centers to the quantum optics. So Jean-François Roch from EMS Paris Saclay, formerly known as EMS
Okay, so many thanks for the introduction and also for the invitation here. So great pleasure. So, so I will describe the properties and the structures of two defects in diamond, and describe how we have used a broad community of scientists that used these defects for both quantum optics and quantum sensing. So, and the first one, which is now well known, is the NV center in diamond, and I like this quotation from Andrew Greentree, who says that in diamond, the NV centers is the worst color centers, except all the others that have been tried. But there are now new other defects like silicon vacancy, tin vacancy, and those kind of color centers that are becoming very interesting, especially for quantum optics purposes. So if we look at first the NV center, the NV center consists of a single substitution nitrogen atom, which is bounded, linked to a nearest neighbor vacancy. And in high concentration, it gives to diamond a very nice pinky color, like, for instance, this famous crystal in the Louvre Museum. Another defect, which was found in man-made diamonds, is a silicon vacancy center, which consists of a silicon atom associated to vacancies. And if you look to their luminescence properties, you immediately see some striking difference. The NV as is at room temperature. The NV center has a very broad luminescence, which starts from the zero phonon line. I will explain what is the zero phonon line at 637 nanometers, and has a width of something of more than 100 nanometers. And you see that the emission of the silicon vacancy is concentrated on its zero phonon line within a few nanometers of line width at room temperature. So the first part of my talk today will be mostly devoted to how we can describe these defects, and more focusing on the NV centers, and tomorrow I will extend that to the silicon vacancy. And the NV centers was well known for a long time, but there was a very important contribution, almost now more than 20 years ago, by Jörg Wartrup and Fedor Zhelezko, who were the first to be able to to isolate single defects in a diamond crystal. And the experiment that you can do to excite and to observe the luminescence of a single defect with standard confocal microscopy is very simple. You see here, for instance, a scheme. You have here the diamond crystal. You have a microscope objective. You scan the light through the microscope objectives. And for instance, either you raster scan the sample, or you twist or you tilt the incoming beam to have this raster scanning of the excitation beam. And after, you detect on each point the luminescence, and you collect it through the same microscope objective. So it's a very simple scheme. And what they found out is already in their very first paper, they highlighted the main properties of that defect. They really behave like an artificial atom, and I will try to explain why we use this term. They have a perfectly stable luminescence at room temperature, and very quickly then people used, like for instance, Philippe Granger group and Kurt Zersifer and Harald Weinfurter in Munich, they build with this from single NV centers luminescence efficient and practical single photon source, for instance, for quantum cryptography. But also a very important feature is that this center, the NV center, has an electron spin in the ground state, which is a very big difference, for instance, compared to single molecules. And you can optically detect the level associated to this spin S equal 1, and you can manipulate this spin using microwave following very standard magnetic resonance technique. So those are the main three properties. And of course, we are in a solid. So, for instance, the NV centers will exist in two charge states. So, as I mentioned previously, we have the electron, we have a nitrogen atom bounded to a vacancy. And if you look to the number of electrons that is left, we have 5 electrons. These 5 electrons will create the NV0 charge state with a spin s equal 1/2. Unfortunately, we cannot use it. We cannot detect the spin s equal 1/2 in the NV0 state. If we simply now add another electrons, we create the negatively charged center, which has a different luminescence spectrum, as you can see here. But now we have 2 electrons, and these 2 electrons will create both triplet state and singlet state. And we will discuss a little bit later how we can, how these spin structures will impact the properties of luminescence of the center. And then, for instance, if we concentrate now on the negatively charged state, the defect structure was proposed by Neil Manson already in the 80s on ensemble, but then after there were a lot of experiments that investigated this scheme at the level of a on the single defect. So basically you have so the spin structure S equal 1, so the triplet state, and the triplet state we have 2 electrons. These 2 electrons will magnetically couple to each other. So this magnetic coupling will remove the degeneracy between spin ms equals 0 and the spin ms equals plus minus 1, which are degenerates. And another point also, which is very important, which is a big difference compared to an atom in the vacuum, is that the NV axis will act as an intrinsic quantization axis. And so we have this spin structure. There is now a splitting of 2.8 gigahertz between them due to this magnetic dipole interaction. And we have the same structure onto in the excited level. So we have these 2 triplet structures, and they are connected together by optical transition, by an electric dipole Alaudi transition, but with, again, differences with what we have in standard atomic physics. The selection rule is delta ms equals 0. This means that we connect ms equals 0 to ms equals 0. We connect ms plus 1 to ms plus 1, and ms minus 1 to ms minus 1. This would be closed transitions. But there is also the singlet structure corresponding to the addition of the 2 spin 1/2 of the 2 electrons in the atoms. And this is a metastable state, which levels are inside connected by electron-phonon interaction to the electric state. But only the ms plus minus 1 is connected toward that level. This means that if now I excite the NV center on this level, it has a chance to go to this level, and in this level it will then decay back both to ms equal plus 1, but most probably to ms equal 0 state. So you see that you have an optical pumping scheme. If you apply green laser light, after a few cycles, all the population will be pumped into the ms equal 0 state. And also the leakage towards this metastable state induces a difference of quantum efficiency of the luminescence from the ms plus minus 1 and from ms equals 0. The ms plus minus 1 is brighter than the ms equals 0 state. Is darker, sorry, has a lower luminescence efficiency compared to ms equals 0 in the excited level. So now, if we simply record the level of luminescence, when we start with all the NV centers pumped into ms equals 0, and we apply a microwave field onto this closed transition in the ground state, we see a bright level of luminescence. And at one point, when this microwave field is resonant with this transition, the population will be transferred to this level, and then we see a drop of luminescence at the resonance between these levels. And then, if we are above the resonance, again, we recover the bright luminescence like that. So we can simply very easily discriminate the 2 levels, and again now observe by simple optical mean the resonance of the NV centers. So this is what is called optically detected magnetic resonance. And now we have everything to play with this spin as a qubit, for instance. We can do radio oscillation. So sorry for the slide in French. We apply a first laser pulse. This pulse pumps the population into MS equals 0 state. Now we have the microwave, which will, for instance, induce radio oscillations between the MS equal 0 state and MS equal +1 state, for instance. And then we apply another laser pulse to have a measurement on which state the system has ended. And we can, like that, observe the radio oscillation. The bad point with this measurement is that it is not a single-shot measurement. So you have to find tricks. If you really want to use this, for instance, for quantum information processing, how can you implement such measurement as a single shot? This is average over many, many cycles. The other point also, which is very important, is how long, if you create a coherence of the spins level, how long will it remain? So this is, for instance, the T2 star time, and you can measure this T2 star time by applying, for instance, a laser pulse first. You apply a pi/2 microwave pulse, which creates a superposition of the spin states, and then you let the system evolve. You apply a pi/2 pulse after that, and then again the readout pulse to measure the spin state. And you will see a decrease of these Ramsey fringes, and the Ramsey fringes, the contrast of the Ramsey fringe, will disappear after a given time T2 star, which is the time for which the coherence can survive, at least without any echo sequence and all these processing. And that can be also engineered and depend a lot in material. If you start, for instance, with a system that embeds a lot of nitrogen impurities, the coherence time is very short, a few microseconds. But if you now eliminate these impurities and both electron spin and nuclear spin, at the end, you can achieve remarkably long coherence time. And again, these are values which are measured at room temperature. So you can prepare coherent state that will survive typically for milliseconds in diamond using this system. Another very important feature of the NV is that if we now apply an external magnetic field, the external magnetic field will split the MS equal -1 and MS equal +1. So instead of measuring one resonance, we now have two resonance peaks with a frequency difference, which is simply the amplitude of the magnetic field. And so using that, we can measure from the geomagnetic factor of the NV, we can measure the magnetic field. And so somehow, using the NV center is a magnetometer with an atomic size, and with a sensitivity, if you look at those curves here, those resonance curves, and their width, the typical sensitivity we can very easily achieve is microtesla. So we can map using that. I will show you later on how this can be done, a magnetic field with a resolution of a few nanometers and this sensitivity. And this is very important, for instance, to map, to characterize magnetic nanostructures. And just one point, this factor is very, very close to the one for a single electron in vacuum, which tells you that really the system, there is almost no spin-orbit coupling which can modify this value of the gyromagnetic factor. So again now, can we understand these features? And another point that I would like now to focus is what are the difference between such what I call artificial atom in the solid state and a true atom in the vacuum. We already seen one. It's the fact that we have this intrinsic quantization axis, which is determined by the N2V axis that gives the orientation inside the lattice. But there are also differences. And to explain a little bit that, I think it is interesting to come back to the pioneer of color centers that were investigated in the 30s. Which are defects in alkali halide crystals. And it was found at the end of the 19th century. So if you take a simple rock salt crystal like this one, and sometimes it has a yellow color. And this yellow color can be produced by irradiation, and for instance, you find that in rock salt mines, which are close to nuclear sites. And you can also create them artificially by, for instance, putting those crystals close to a nuclear reactor, a real one, and you will produce these colors. And the color will change a lot depending on what kind of alkali halide you consider. This is rock salt and other, KCl, potassium bromide, and you see different colors. But if you look to the absorption spectrum, they behave almost the same. They have almost the same width. And you can also produce this coloration by completely other techniques that was developed by Robert Paul in Göttingen in the 30s. So you take, for instance, a KCl crystal here. You put it in a glass tube in vacuum, sealed, and then you put here some potassium metal and you heat it to its vapor pressure. And if you wait, you will have this coloration of the crystal that will appear. So somehow the potassium atoms will have entered into the lattice and create these colors. So there were a lot of debate of how we can understand what is the physical origin of these colors. But all these materials are first very wide bandgap semiconductors. If you look to the bandgap of these materials, it's typically above 5 eV. So if you take a pure crystal, it will be perfectly transparent. Now, in other materials, we have different kind of bandgaps, for instance, diamond and silicon carbide, which are two in which people now there are a lot of works to investigate defects in those two wide bandgap materials. People are also considering those ones. There are a lot of works where people try to investigate the structures of those defects in this wide panel, this broad panel of materials. So let us consider the difference between two types of defects. The first one is phosphorus in silicon, and the second is one of those alkali halide crystals. I'm sorry for the bad picture, but you see here as a function of the energy increases in this direction. Here we have the absorption, which is from the valence band to the conduction band. And you see here, when isolated below this transition, the absorption band from the defects. So let us, for instance, consider phosphorus in silicon. So phosphorus will dissolve in the silicon sites, and there is one more electron in phosphorus atom than in silicon. And we will have 4 of these electrons coming from the phosphorus that will create bonds with the 4 nearest silicon atoms. And you have 1 electron left. And the 5th electron left, due to the fact that phosphorus will be a donor close to the conduction band at a frequency difference of something like 35 millielectron volts, can very easily go into the conduction band. So it can be ionized. But at low temperature, the electron can also remain bounded to the phosphorus nuclei. And so you have a kind of simple structure, which is an hydrogen-like atom, which, of course, is modified by the lattice. And this was developed, a model of that was developed already in the 50s by Kohn. And so we can describe this electron as trapped in the lattice with an effective trapping potential. Like this is the potential for the hydrogen atoms, and we simply take into account the screening factor due to the fact that the electron will be delocalized over many sides of the crystal. And so we have an effective Bohr radius for this hydrogen-like structure. And so, for instance, phosphorus in silicon, it is well known that it can be a very good localized qubit, and you can have interaction between 2 phosphorus impurities and an electrical readout of the state of that. And there were proposals by Kane and a lot of development along the ID following this very simple description. Of course, this, if you think a little bit, this will not work for our defect. With that, we cannot explain why we have this transition well isolated for the defects in alkali halide within the bandgap. So it does not work. We have to find something else. So let's start by the simplest crystal defects we can imagine. It's simply a vacancy. So a vacancy can be produced very easily. I heat the crystal, or I put it under an ion beam. And so the ion, when they will come inside the lattice, one of the atoms of the lattice will go on the surface, and there will be a vacancy removed in the crystal. That was called, that is well known, that is called the Schottky defect. And this Schottky defect exists even at thermal equilibrium. There are, if you need to minimize the free energy of the crystal, you will add disorder, and the disorder will come from those vacancies, and you have always a kind of number of vacancy that exists in the crystal due to that. But you can, of course, be out of equilibrium and add more vacancy than what is here. If you now have a relatively open crystal, such as diamond, you can have space between the atoms so that one of those atoms can be transferred from the lattice into an interstitial position. And then, for instance, you can have a kind of bonding between this interstitial atom and the vacancy it left when it was moved, and that is called the Franck-Condon defect, which consists of this bonding between these two systems. So this is really the most simplest structure you can imagine. So now let us come back to the alkali halide crystal. In the ionic crystal, we have here this vacancy, but then you have to imagine that this is a plus ion, a negative ion, plus ion, etc. So if you have a vacancy, you are not in an electrostatic equilibrium. So what can happen, for instance, if you have removed a chloride atom, then you need one negative charge. And so to compensate the extra positive charge, you can trap an electron inside this vacancy. So somehow, if you start with this idea, you can imagine that you will have single electrons trapped in the vacancy and somehow in a box which is created by the surrounding positive ions. And if you look at that, whoops, sorry, goes the wrong direction. We can do a very simple model where we will confine the electron in a box, like a 3D quantum well, where we have the parameter A is simply the lattice spacing of the crystal, and we simply have now to calculate the two first level of energy of the electron inside this box made by that. So if you do the calculation, of course, you all know how to do it, but let's take again the formula. So I take my 3D box with lattice parameter A, and then the fundamental level, depending on X, Y, and Z, I can write it and this state is non-degenerate, J equal 1, and its energy is E1 equal 3 pi square h bar square times 2m a square. And m is the mass of the bare electron, not an effective mass in the crystal, in this very simple model, a naive model. Now, if I calculate the second energy state. I will have now a state which has a degeneracy of 3, and it will be the same. So this is called Z. And the energy E2 is then 6 P square H bar over 2 M A square. So the difference between the two energy levels is then so this is a law which tells us that A minus, and if I take the two parameters, using this, I will find that this parameter, if I explain the energy, the difference of energy in electron volt and the lattice spacing in angstrom, this parameter, if you do the calculation, is 1 over 33. And so when you see, sorry?
But there should be two length scales. I mean, it can be the sodium or the chloride removed, and then the oxide has different size, right?
Ah, okay. I see what you mean. Yeah, but usually it's the chloride that is removed more easily than the other one. Don't really know why. Not able to explain that. So if we compare with this formula, we see that we have the good power dependence as a function of the lattice parameter. And simply now, if we change a little bit the size of the box, we can imagine, for instance, that the electron is produced by by overlapping onto the positive ions around the electrons. So if we adjust now to the experimental data by simply this correcting factor 1 over 1.33, you see that you have a very good agreement of between what is observed experimentally. And this was also confirmed, this structure, that it is one trapped electron to explain the F centers, was also explained by electron paramagnetic resonance, where they measure the J factor in this experiment, which was again very close to the one of a free electron. And the slight difference can be attributed, can be computed by taking into account the spin-orbit coupling. You have the spin of the intrinsic spin of the electrons, and here you will have the orbital also angular momentum, and the two will couple, and this coupling will create these parameters. So you see that we have we have something which is very simple to understand. Of course, it's a toy model, so it can perhaps be sounds a little bit naive. Another important feature that we have to explain is the luminescence properties. We have both the absorption here, and if we look at the emission, we see that in these centers, like in the defects in diamond, there will be always the emission occurring with a very large Stokes shift. And this is characteristic of the very strong interaction between the electron that creates the F center and the lattice. This is old measurement, but you see that you have, again, the same emission line as the absorption line, but now with a very strong shift. This is, for instance, you have absorption in the yellow for yellow wavelengths, which produce the blue color of the crystal, and the emission will be in the infrared. And there were a lot of interest back in the 80s of using these color centers for making dye laser, the equivalent of dye laser in the infrared before semiconductor diode lasers were available, and also before the titanium sapphire laser. And the main issue with that is the fact that you have to keep those crystals at low temperature, so that you had to put the crystal in a cryostat, build a laser around it, and also after a while there were a bleaching process, and the crystal was not working anymore. You had to change it, to irradiate it again to create the color and all that. And then all that was completely removed in a few years by the advent of diode lasers and titanium sapphire laser. But that was the only way to make a dye laser for atomic physics back in the 70s and 80s for addressing transition in the infrared. So how can we explain that? And this can be explained by what is a very general effect in solid-state physics, which is called the Jahn-Teller effect. And the Jahn-Teller effect is something a little bit mysterious, at least for me. If you have something that you do not understand, you invoke usually the Jahn-Teller effect. And the idea beyond the Jahn-Teller effect is that is taken from a book, textbook. A molecule with strong symmetries has degenerate states. Yes, okay, so it's exactly that model. I started with my electron in a box. We see that the second level has a degeneracy of 3. And then if now I envision the effect of a distortion of the molecule, this will of course lead to a lower symmetry. And the lower symmetry of the system, that's the general rule, will lift the degeneracy and stabilize the molecule at a lower energy than the distortion, than without distortion. So we can try to mimic this effect using our toy model of the electron in the box by simply taking my cubic box from the start and now changing its size and transforming it into this. So I introduce a distortion parameter, and now I can calculate, it's not very difficult, to calculate the new wave functions with this configuration. And if I do that, what I will find is I will effectively, by distorting the size of the crystal along the z-axis, now I create, starting from this threefold degeneracy, I have one state along the z-axis which is not degenerate, and another state along the x or y-axis which are degenerate and with the same energy. So I have indeed changed a little bit the system. And this is somehow, again, a toy model for the Jahn-Teller effect. And if I calculate, this is not very difficult. It's simply a little bit boring. If you evaluate the energy of those defects as a function of this parameter, B over C, so the distortion of the crystal, you have those kind of curves. So the level E'1, if you looked to its lowest energy for that level, the lowest energy is realized by eta equal 1. This means that the cubic box. So for the ground state, the best symmetry of the molecule is this one, the cubic symmetry for my electron, and I have the lowest energy. If now I have some distortion, this distortion appears with cost me an extra energy. If I look to the two other levels, I see now that again this is the second level of the box would be here in E1 unit. So I see that for both these two levels, I have an energy which is slightly below this energy that I calculated in my cubic box. So this is again the effect of the Jahn-Teller effect. I have introduced a distortion of the molecule, and this distortion at the end led to a decrease of the energy. And but this means that, for instance, the equilibrium state for which I would have the lowest energy will be different for the ground state than for the excited level. This is exactly the message of the Jahn-Teller effect. So these, if you look at that and those curves, these curves are exactly somehow the one that you calculate in molecular physics when you want to measure the potential of the electron inside the molecules. And this naive model somehow allowed me to calculate the potential that will then induce the quantization of the mode of vibration of the crystals. And the two also, what is also important, and we have to keep that in mind when we will talk about the dipole of the NV centers, the electric dipole of the dipole, the two transitions will have different electric dipole. The electric dipole from this transition will be polarized along Z, the Z-axis, whereas the transition from this state to the other state will be polarized in the perpendicular plane. Yeah, sure.
I'm a little confused. I mean, at 1, eta equal 1, you have the degenerate state.
This one is a...
Eta equal 1, the x-axis.
Yes, this is eta equal 1.
But if you now make a distortion, one
yes.
goes up and the other one goes down. And in your picture, both go down.
No, this is 1. This is 1.
But the E2, the excitable 2?
This one?
At the crossing. I mean, here's the crossing, yes? E2.
Here?
Yes. So this is without distortion. Now if you make a distortion,
yeah.
then one goes up. And the
one goes up. So yes, one goes up a little bit, and the other down. But it means also that I can have, depending on the transition I will not end with the same distortion in the upper excited state.
On the left, both go down.
Ah, yes, sorry, this is confusing. I agree. Thanks.
There's no secret.
Yes, I did that. Thanks. No.
Okay,
it can be lower. Here it can be lower. For this value. No, I don't really see what you mean. I'm sorry.
Depends if you are plotting for a given value of theta, so Robert is right, because if you are plotting the minimum value of the transitions,
Ah, okay. I see what you mean. Okay. We can discuss after. Okay, but with that, if I take these two values around that, which is quite fascinating with very simple model, for me at least, is I can calculate, for instance, this parameter, and again, this parameter. So if I take that, and I compute the two, I make the calculation, when I look at that, I am actually very close. Instead of finding 0.45 from the experimental value of the Stokes shift as a ratio of the two energy, I will found 0.4. So just by this very crude model. So somehow now we can understand the luminescence spectrum by simply applying the Franck-Condon principle that we all know. We start from the quantization of the crystal vibration as a function of this parameter. And again, from the ground state, we have a perfect cubic symmetry, eta equal 1. And now we have transition from all those levels. But we see that when it goes to the upper level, it will be not the fundamental of energy of this level. That means that the system will distort. There will be a distortion of the crystal, and this relaxation by emission of many phonons in the crystal to end into this excited lowest phonon level. And after, again, it can decay back to the ground state and after that, again, it will have very quick relaxation by emission of phonons toward the relaxation state where we have, again, this non-disturbed box. So this, again, is very crude, but we can, like that, understand at least the Stokes shift and have reasonably good parameters from that. And the same will always apply to all defects in the solid state. So you have to keep in mind that compared to an atom, you will not have the same symmetry it's more complicated. The symmetry in the excited level is very different from the symmetry in the ground state. And what you learn in standard atomic physics in the textbooks is not exact, cannot be applied to defects in the solid state. It gives you some bad intuition many times. Oops, sorry. Now, nevertheless, what is also amazing is now if I play only with the ground state, and for instance, I am back to the NV centers, I can describe the interaction of the center with fields such as a magnetic field or strain in the lattice as a very simple Hamiltonian. Somehow I don't know if this Hamiltonian is really true, but in an inductive way, it works very well to explain the experiment. So what I will put like that to explain, accounting for my level structure that I explained before, I should perhaps explain that again. I'll write it on the blackboard. So I have here ms equals 0, the two level ms equal plus minus 1, the same structure in the excited level associated to spin. So you have to take into account the fact that you have to remind that this is a spin structure, so somehow related to the intrinsic degree of freedom of the NV center. And this is and you have also the optical transition, and the two somehow are decoupled. So if I now look to the effect of a perturbation inside the ground level manifold, I can, for instance, apply, so what I will have is simply this first Hamiltonian to describe this state, D0 is Z square, where D0 is this parameter in frequency, so something like 3 gigahertz. And if now I apply a magnetic field, by the Zeeman effect, I will shift these two levels, and this is my second term. The gyromagnetic factor, the spin, and the applied magnetic field. So this is the Zeeman term that I wrote it here. But I can do other things also. The defect is in the lattice. I can play with strain on the lattice. And I have very different strain, and different type of strain will have different consequences on the level structures. Suppose, for instance, I have an hydrostatic compression. I will then keep the full symmetry of the defect. This means that these level structures will remain identical in this hydrostatic compression. And so this somehow will simply put the two electrons in the negatively charged centers closer. Their magnetic interaction will be increased. And so the separation of these two levels here, of these levels, will increase. So, so I can write down as this parameter like that. D parallel, meaning that I am along the axis of the defect, keeping its symmetry. So a strain parameter, the strain component, the lattice strain epsilon z, and then sz square, the same term as the one for the Zeeman effect. But I can also have a transverse strain that is applied to the crystal. And then in that case, the symmetry of the defect will be strongly modified. And this is a little bit more tricky to write, and it's the second term that I write here. I will then couple, due to this transverse strain, I will mix these two levels. And now you can convince yourself that the good eigenstate will be not anymore plus or minus 1, but will be a linear combination of those states. and I can write the Hamiltonian to create that. So this is simply an Hamiltonian which makes exactly this effect. So 2 times, so this is. But somehow, again, this is completely inductive. I have written the Hamiltonian to somehow explain the result of my experiment. And there are a lot of works, especially using ab initio calculation or group theoretical method, to try to explain that, or to derive more complicated description of this Hamiltonian for the interaction. Yes?
So the transfer strain will not lead to a complete mixing like this. It will be 1 plus eta by epsilon of -1. Or it will be just a small admixture. Or
No.
it will completely
It mixes the effect. But this is in absence of the other one. I see what you mean. If I have a transverse strain, the good, so again, I do not write the full eigenstate of this Hamiltonian. I write the Hamiltonian that would be the eigenstate of only this part. So I will have a competition between the eigenstate of this. You see what I mean? So you have the 2 effects. Okay, perhaps I should skip that. The other point also is that you want to use those defects. And so can you create them? So I show you how they can be created in bulk, as ensembles, like for instance, irradiation in alkali halide crystals. What has been developed is a lot of new techniques now that has been investigated and that now available to engineer NV centers and all defects in diamond or in any wide bandgap materials by different kind of techniques. Either you create them during the growth or you add them as extra impurities, for instance, using ion implantation. And this is, for instance, a system that we developed in our group where we have a FIB machine, so it's a focused ion beam. We are able, like that, to implant, for instance, pure nitrogen impurities. So we start with a crystal, which is a perfect diamond crystal, has no impurity at all. We can shoot nitrogen atoms at specific location in the crystals. And after, when the nitrogen impurities will enter into the lattice, at the same time, you will create vacancies. At that stage, we do not have the NV that has been created. You simply anneal the crystal. The vacancy, as I explained at the very beginning, will have some, will move, and after that can recombine with the nitrogen impurities to create the NV centers. And for instance, what you see here, it's a diamond anvil. I will explain why we choose that while we're working on that. And on top of it, on the cullet here, which has a size of typically 100 micrometer, we can create a pattern of NV centers. Each of those spots has typically 10 NV inside. And this technique is now currently used in many groups. For instance, if you change here the source, here we have a plasma source that creates, from which we extract nitrogen atoms. It can also be a metallic source, with a silicon tip. And from the silicon tip, you can extract silicon ions and create silicon vacancy center using exactly that technique. And the good point is that you do not have to go to an accelerator to create this defect. You can have really in the lab next door. And the typical resolution that now people are able to do is to create defects below 10 nanometer spatial resolution. And they can, for that, you have a lot of works where people have been able to couple efficiently defects to photonic nanostructures. Okay, why we are interested in it is we want to use the NV center and the magnetic sensing properties. These influence to a of a magnetic field to investigate the magnetic properties at high pressure. This is not very important in the context of this lecture, but for the typical system that people use to reach very high pressure, it's called a diamond anvil cell. So you have two diamond anvils, and you squeeze them against each other, and with a confinement associated to a metallic gasket, you can create inside the chamber, you can reach pressure that are up to now be above 500 gigapascal, so a few megabars. The pressure in the center of the Earth is 300 of gigapascal. So you can achieve that, and people are there are a lot of excitement at the moment because, for instance, at those kind of pressure, you predict new phase, such like everything becomes metallic somehow, and perhaps even superconductor. And this a key example is hydrogen, for instance. So there are a lot of interest of investigating that, but again, after that, you would like to make some measurements inside, and you can imagine that if you put, for instance, electric contacts inside that, when you squeeze everything, the reliability of your measurement is a problem. Okay, but nevertheless, this is not what I would like to explain. So if we look now again to the behavior of the spin resonance of the NV, what we observed is that we will have, for instance, the line that is observed at 9 gigapascal, and it's exactly that. It's simply shifted by the pressure, so the hydrostatic pressure. So we see a shift of the line, and somehow the NV center is also a pressure sensor. We can measure in situ the pressure with that, and there are a lot of applications perhaps around this idea, especially in systems where it's not easy to measure pressure. And at the same time, you will see that there is another line that appears. The line splits into two components, and this is the effect of the transverse strain that is applied here. But if you see that, there are a lot of things that we do not understand. From a naive model, I would expect that the two lines will have the same component. This is not what we observe. The lines, when we apply both the strain and an extra magnetic field, has also very specific behavior. So somehow we need to go beyond this simple description, and so we need a model to understand how the perturbation will be applied influences these levels. And for instance, we have a lot of still open questions. The strain modified, for instance, the leakage toward the singlet manifold that create the spin polarization. This is an open question. So there are many things that still, even on this system that has been now studied for the last 20 years, remains unknown. And we need to do that, to go back to the NV quantum structure, and this will be the topic of my second talk, of the talk tomorrow. But just to give you an idea about that, we will come to another description of the defects, which was actually pointed out by Neville Mott in the 30s. It is quite fascinating to see that back in the 30s, people really did not understand the origin of the colors of this alkali crystal. It was a big problem. And even Landau gave a wrong answer. He was explaining that you had the electrons moving, and the electrons was somehow moving all over the positive and negative charge of the crystals and creating a polaron. And what you are observing is the specific feature of this polaron. And Neville Mott explained, no, Landau is wrong. And he pointed out that no, you have to take another approach, which is more from molecular physics. If you take a perfect crystal, you have the translational periodicity, the electron moves in all that, in the average field of the electrons and nuclei, and we all know that then we describe the electron by a block state delocalized on the whole crystal. If we now take this localized vacancy and do not go a little bit further compared to my simple model, the symmetry is reduced to rotation and reflection. And then the absence of an atom will leave unpaired electrons. So I have dangling bonds here, and I can make like what I learned in molecular physics. I can create the defect by mixing these dangling bonds. And this will be the topic of the talk tomorrow, where we will try to describe the NV centers as really as a molecule built from all these dangling bonds that we have here. And we will see how we can have the combination of these orbitals to create, to reproduce exactly this structure that we have here. And then there are a lot of works also. This is a kind of approach which is quite simple. You can go again beyond that. You can do, for instance, the Hubbard model. You can apply Hubbard model to construct the structure about that, or you can use differential functional theory again to create all that. And there are a lot of people now. We are trying to apply those tools to describe the physics and of defects in materials as broad, like, for instance, gallium phosphorus or all those kind of systems. It's again revisiting somehow the physics of defect, which was a huge field of solid-state physics in the 60s, with the new eye of single defects and their atomic-like properties. But again, you always have to think that there are strong differences between what we learn in atomic physics and when we try to apply it to a solid-state system. And understanding that is not always very easy, at least for me, perhaps with other people it's easy. Thank you for today. So I think. This will be tomorrow.